Right now, at this very moment, you are traveling through space at breathtaking speeds. You might feel perfectly still, nestled under your covers, but you're actually hurtling through the cosmos at nearly 67,000 miles per hour as Earth orbits our Sun and our entire solar system. It's racing through the Milky Way at over 500,000 miles per hour. Yet here you are, feeling wonderfully, peacefully still. Welcome to Sleep About Science. Tonight we're drifting into the infinite expanse of deep space, where the most extraordinary phenomena unfold in perfect, eternal silence. And if you drift off to sleep while listening, that's perfectly wonderful. In fact, there's something rather poetic about falling asleep while contemplating the universe. After all, sleep itself is a kind of journey into the unknown. Before we begin, please make yourself comfortable. Pull your blankets a little closer, adjust your pillow just right, and let your breathing slow. Remember, this is educational content, not medical advice. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into science. Now, wherever you are in the world, whether it's late evening, deep night, or early morning, let's embark on a peaceful voyage to the farthest reaches of space. Imagine for a moment that you could step outside not just your house, but outside our entire solar system. You'd find yourself in what astronomers call the local bubble Michels, a region of space carved out by ancient stellar explosions, stretching roughly 1,000 light-years across. It's like standing in a vast cosmic clearing in a forest of stars and interstellar dust. This bubble surrounds us with space so thin, so empty, that it contains only about 1 particle per cubic centimeter. To put this in perspective, the air you're breathing right now contains about 25 billion trillion particles in that same space. But this apparent emptiness is deceiving. Deep space isn't truly empty at all. It's filled with invisible rivers of magnetism, ancient light from the birth of the universe, and whispers of cosmic events that happened billions of years ago. Every breath you take contains atoms that were forged in the hearts of dying stars, scattered across the galaxy, and somehow found their way to Earth, to you, to this very moment as you listen to these words. The silence of space would be absolute. Unlike Earth, where sound waves travel through air, space lacks the medium for sound to propagate. If you could somehow survive in the vacuum between stars, you could witness the most violent cosmic explosions in complete, profound silence. A supernova that outshines an entire galaxy would unfold before you like a silent movie, its light reaching you in waves of color and radiation, but producing no sound at all. There's something deeply calming about this cosmic quiet, the universe conducting its grandest symphonies in perfect silence. Let's drift further out, beyond our local bubble, into the spiral arms of our galaxy. The Milky Way stretches 100,000 light-years from edge to edge, containing somewhere between 100 and 400 billion stars. But from our perspective, floating in deep space, the galaxy would appear as a gentle, glowing disk, its spiral arms traced in the soft blue light of young stars and the warm red glow of stellar nurseries where new suns are being born. You might imagine that space between the stars is pitch black, but your eyes would slowly adjust to reveal the faintest of glows. This is starlight that has traveled for millions of years, mixed with something even more ancient, the cosmic microwave background radiation, the afterglow of the Big Bang itself, still warming the universe to just 2.7 degrees above absolute zero. You would literally be seeing the baby picture of our cosmos, stretched and cooled by 13.8 billion years of cosmic expansion. Floating in this vastness, time would seem to stretch and slow. Light from the nearest star beyond our sun takes over 4 years to reach us, meaning that starlight touching your imaginary face would be showing you the universe as it was years ago. The Andromeda galaxy, our nearest galactic neighbor, appears to us as it was 2.5 million years ago, when our earliest human ancestors were just learning to use tools. In deep space, you become a time traveler, seeing not the universe as it is, but as it was. The most distant objects we can observe with our telescopes show us galaxies as they appeared over 13 billion years ago, when the universe was still young and wild, forging its first stars in brilliant bursts of creation. These ancient galaxies appear to us as tiny, faint smudges of light, but each one contains hundreds of billions of stars, planets, and perhaps even other forms of life, all existing in a time so remote it challenges our ability to truly comprehend it. Between these vast islands of stars lie even vaster oceans of space. The distance between galaxies is measured in millions of light-years. To cross the space between the Milky Way and Andromeda at the speed of light would take 2.5 million years. At highway speeds, it would take longer than 30 billion times the age of the universe. These scales are so immense that they become almost abstract, numbers so large they lose meaning and transform into something closer to poetry. Yet within this seemingly endless void, matter organizes itself into the most beautiful structures. Dark matter, invisible but present, creates scaffolding throughout the universe, guiding the formation of what astronomers call the cosmic web, minest vast filaments of galaxies, stretching across billions of light years, connected by gossamer threads of gas and dark matter, with enormous empty regions called cosmic voids nestled between them. From far enough away, the universe would look like a delicate three-dimensional spider's web, shimmering with galaxies instead of dewdrops. In the deepest regions of space, where galaxies are separated by hundreds of millions of light years, the universe becomes extraordinarily peaceful. Here, the cosmic expansion becomes the dominant force, gently stretching space itself. New space is literally being created between distant galaxies, not pushing them apart through any force, but simply expanding the fabric of reality itself. It's as if the universe is slowly, quietly breathing outward, creating more room for itself in a process so gradual it would be imperceptible even over millions of human lifetimes. These cosmic voids, the largest empty spaces in the universe, contain almost nothing, like perhaps one galaxy where a typical region might contain hundreds. They are so large that light takes hundreds of millions of years to cross them. If you could somehow find yourself in the center of one of these voids, the nearest galaxies would be so far away they would be invisible to your naked eye. You would float in an ocean of darkness so profound that the only light would come from the faint afterglow of creation itself. But even in these empty regions, invisible processes unfold with infinite patience. Virtual particles pop briefly into existence and disappear again, borrowed against the uncertainty principle of quantum mechanics. Dark energy, that mysterious force driving the expansion of the universe, works its gentle magic, stretching space at the smallest scales. Even in apparent nothingness, the universe is alive with possibility. The temperature in these deepest regions of space hovers just above absolute zero means, not because space is actively cold, but because there's simply nothing there to generate heat. Without matter to absorb and re-emit energy, without stars to warm the void, the universe settles into its natural state of peaceful, profound chill. It's the ultimate quietude, the cosmic equivalent of that perfect moment just before sleep, when your body completely relaxes and your mind begins to drift. Consider the strange beauty of cosmic time in these regions. Without nearby stars or galaxies to provide reference points, without the usual markers we use to measure time, moments would stretch into eternities. The expansion of the universe would be the only clock ticking so slowly that billions of years would pass like seconds. In the deepest voids you would exist in a realm where time itself becomes negotiable, where the usual urgency of existence gives way to cosmic patience. The story of these empty spaces is also a story of what will come. As the universe continues to expand and dark energy drives galaxies further apart, more and more space will eventually look like these vast voids. In the far future, trillions of years from now, when the last stars have burned out and the universe has grown cold and dark, most of space will resemble these quiet regions, peaceful, patient, and profound in their simplicity. But that future is unimaginably distant. For now we exist in what astronomers call the stelliferous era, when stars still shine and galaxies still dance their slow gravitational ballet across the cosmos. We live in a time when the universe is still young enough for complexity, for beauty, for the extraordinary chemistry that makes life possible. We are here during one of the most interesting epochs in cosmic history, when matter has had time to organize itself into planets and people, but before entropy wins its final victory and everything settles into peaceful equilibrium. From our perspective, floating in deep space, Earth would be completely invisible, lost in the glare of our sun, which itself would appear as just another star among hundreds of billions in our galaxy. All of human history, every story ever told, every life ever lived, every dream ever dreamed, would be concentrated in a point of light too small to see from just a few light years away. Carl Sagan called Earth a pale blue dot, but from the depths of intergalactic space, even that generous description would be too grand. This perspective shift has a way of putting things in context that's both humbling and oddly comforting. The concerns that keep us awake at night, the worries that chase us through our days, the anxieties that sometimes seem overwhelming, all of these exist on a tiny, beautiful world floating in an ocean of space so vast that our entire solar system wouldn't even register as a speck of dust. There's something profoundly peaceful about this realization, something that invites a kind of cosmic calm. Yet this vastness doesn't diminish us or make us insignificant. Instead, it makes us remarkable. In all this emptiness, in all these billions of galaxies and trillions of stars, we represent something extraordinary, matter that has organized itself in such a way that it can contemplate its own existence. Atoms arranged so precisely that they can wonder about the cosmos that created them. We are the universe's way of thinking about itself, consciousness arising from the same materials that drift silently through the cosmic void. The light from distant stars that took millions of years to reach us is the same light that falls on your face when you step outside on a clear night. You are directly connected to the cosmos, not through some mystical process, but through the most ordinary physics moist as photons that began their journey when the universe was younger, that traveled across unimaginable distances through perfect vacuum, just to end their journey in your eyes. Every time you look up at the night sky, you are seeing across both space and time, directly observing the deep structure of the universe. In the cosmic web that connects all galaxies, our local group, the small cluster that contains the Milky Way, Andromeda, and about 54 smaller galaxies, is moving through space towards something called the Great Attractor, a gravitational anomaly lying 150 million light-years away. We're all part of an even larger structure called the Virgo supercluster, which itself is being drawn toward an even larger collection of galaxies called the Shapley supercluster. These movements are slow beyond human comprehension, but they connect us to cosmic structures on the grandest scales imaginable. The invisible dark matter that makes up most of the mass in the universe creates halos around every galaxy, extending far beyond the visible stars. These dark matter halos are like cosmic cocoons, gentle and protective, helping to shepherd the formation of stars and planets. Although we can't see dark matter directly, its effects are everywhere, a kind of cosmic scaffolding that holds the universe together through pure gravitational patience. Between galaxies in the vast spaces we're imagining ourselves floating through, the cosmic microwave background radiation creates the universe's ambient temperature. This ancient light has been traveling for nearly 14 billion years, cooling as the universe expands, until it now provides a gentle warmth of just 2.7 degrees above absolute zero. It's as if the entire universe is wrapped in the faintest, most gossamer blanket, woven from the light of creation itself. In these quiet regions between the galaxies, space itself participates in the grand expansion that began with the Big Bang. It's not that galaxies are racing away from each other through space, but rather that new space is being created between them, like ink dots on a balloon that's being slowly inflated. The expansion is so gentle, so gradual, that within our own galaxy, within our solar system, within the space between atoms, it's completely negligible. But on cosmic scales, it's the dominant process shaping the architecture of everything. This expansion means that the most distant galaxies we can observe are moving away from us at speeds that approach the speed of light, not through any force pushing them, but simply because so much new space is being created between us and them. Eventually, these galaxies will cross what astronomers call the cosmic event horizon, beyond which their light will never reach us. The universe is constantly creating new regions of space that will forever remain beyond our ability to observe, adding layers of mystery to the cosmic story. Yet even as the universe expands and galaxies drift apart, the fundamental particles that make up everything the quarks and electrons, the neutrinos and photons remain exactly the same as they were at the moment of creation. The electron in your body is identical to electrons that exist in the farthest galaxies, following the same laws of physics, participating in the same quantum dances. There's a deep unity underlying all the apparent vastness and separation. The neutrinos streaming through space right now are passing through your body at this very moment. Trillions of them every second, most of them created in the hearts of distant stars, some of them relics from the Big Bang itself. They barely interact with matter, passing through entire planets as if they weren't there, connecting every point in the universe in an invisible web of nearly massless particles that have traveled for billions of years without stopping. Some of the most peaceful phenomena in the universe unfold over timescales that dwarf human comprehension. Galaxies merge in slow-motion ballets that take hundreds of millions of years to complete. When the Milky Way and Andromeda eventually collide about 4.5 billion years from now, it will be less of a collision and more of a gentle gravitational dance. With stars passing by each other like dancers in a cosmic waltz, the night sky slowly transforming over geological ages. The black holes scattered throughout the universe sit in patient meditation, warping space and time around them in perfect mathematical curves described by Einstein's equations. Even the most active black holes, the ones actively feeding on surrounding matter, do so with a kind of cosmic restraint, creating jets of material that stretch for thousands of light years while maintaining perfect symmetry and balance. In the depths of space between the stars and galaxies, the vacuum itself is alive with quantum fluctuations, tiny temporary violations of the conservation of energy that create particle-antiparticle pairs that immediately annihilate each other. These quantum foam bubbles are so small and brief that they exist below the threshold of direct observation, yet they represent the universe's way of staying dynamically balanced even in apparent emptiness. The cosmic web of dark matter that connects all visible structures in the universe operates like a vast, slow river system, channeling the flow of ordinary matter along invisible currents. Gas falls along these dark matter filaments toward the intersections where galaxies form, like leaves following streams toward lakes. This process has been ongoing for over 13 billion years, patiently building the large-scale structure we observe today. In the coldest regions of intergalactic space, temperatures can drop to just a fraction of a degree above absolute zero. At these temperatures, the few atoms that exist move so slowly that quantum mechanics begins to dominate their behavior. In some regions, hydrogen atoms exist in a quantum superposition state, neither fully here nor there, existing in a kind of probability cloud that fills vast regions of space with ghostly potential. The magnetic fields that thread through intergalactic space are incredibly weak but stretch across enormous distances, creating a cosmic nervous system that connects galaxies across millions of light years. These fields were likely created in the early universe and have been slowly growing and evolving ever since, carrying information about cosmic events across the largest scales imaginable. Sometimes high-energy particles from distant galaxies travel across billions of light years to reach us, arriving as cosmic rays that pepper our atmosphere. These particles have crossed most of the observable universe, surviving encounters with magnetic fields, shock waves from stellar explosions, and the general hazards of intergalactic travel to deliver messages from the most distant corners of creation. The most ancient light in the universe, the cosmic microwave background, fills all of space with a gentle glow that represents the moment when the universe first became transparent, about 380,000 years after the Big Bang. This light has been traveling for over 13.8 billion years, cooling and stretching as space expands, but still carrying the faint echo of creation. Every cubic centimeter of space contains about 400 of these ancient photons, invisible to our eyes but detectable to sensitive instruments. As you contemplate these vast scales and long time scales, notice how they invite a different relationship with time itself. In cosmic terms, human lifespans are brief flickers, but they're flickers that burn bright with consciousness, awareness, and the ability to contemplate the very universe that created us. We exist at the intersection of the quantum and the cosmic, large enough to contain multitudes but small enough to feel intimately connected to each other and to the cosmos. The expansion of space means that the most distant galaxies appear to us as they were when the universe was young and wild, still forming its first generation of stars. These ancient galaxies are like cosmic seeds, showing us the raw material from which all later complexity would grow. In the deepest images captured by our most powerful telescopes, we see thousands of galaxies stretching back to when the universe was less than 1 billion years old, each one representing billions of stars and potentially countless worlds. Even in the vast emptiness between galaxy clusters, occasional rogue stars wander in the darkness, ejected from their home galaxies by gravitational encounters. These lonely stars carry their planets with them, creating isolated solar systems floating in intergalactic space. On worlds orbiting these exile stars, the night sky would be almost completely black, except for the faint glow of distant galaxy clusters, creating a perspective on the universe unlike anything we can imagine from our position within the Milky Way. The process of cosmic expansion is so gentle that it would be undetectable to any local observer. Someone living in a galaxy billions of light years away would see their local stars and planets behaving normally, held together by gravity and electromagnetic forces. Only on the largest scales does the expansion become apparent, creating more space between galaxy clusters while leaving the internal structure of galaxies essentially unchanged. This expansion also means that the observable universe minors the sphere of space from which light has had time to reach us, since the Big Bang theory has a definite edge. Beyond this cosmic horizon lies more universe potentially infinite in extent, but forever beyond our ability to observe. The light from these distant regions simply hasn't had enough time to cross the expanding space between us and them. In this sense, we live in a bubble of observability surrounded by mystery. The beautiful spiral patterns of galaxies like our own Milky Way are created and maintained by density waves, regions of slightly higher gravity that sweep around the galactic disk like slow, invisible arms, triggering star formation as they pass. These waves move much slower than the stars themselves, creating the illusion of stable spiral arms while individual stars orbit in and out of them over millions of years. In the cores of galaxy clusters, the space between galaxies is filled with hot, thin gas heated to millions of degrees by the gravitational energy of the cluster itself. This intra-cluster medium glows faintly in X-rays, creating enormous halos of superheated plasma that extend far beyond the visible galaxies. Despite being millions of degrees hot, this gas is so thin that you could pass through it without noticing. It's hot because the few particles present are moving very fast, but there are so few of them that they carry very little total energy. The cosmic web that connects all large-scale structures in the universe resembles, in some ways, the neural networks in living brains, vast filaments connecting nodes of concentrated matter, with enormous empty regions between them. This similarity might be purely coincidental, or it might reflect some deeper organizing principle that operates across all scales, from the quantum to the cosmic. Dark energy, the mysterious force driving the acceleration of cosmic expansion, remains one of the deepest puzzles in modern science. It appears to be a property of space itself, becoming stronger as the universe expands and more space is created. Unlike matter and radiation, which dilute as space expands, dark energy maintains constant density even as new space appears. This means that its total influence grows over time, gradually taking control of the universe's fate. The cosmic microwave background radiation provides a baby picture of the universe when it was only 380,000 years old, showing tiny temperature fluctuations that would eventually grow into all the large-scale structures we see today. These fluctuations were incredibly small, Mitres variations of only about 1 part in 100,000 mundium, yet they contained the seeds of every galaxy, every star, every planet, and ultimately every living being. In the deepest voids between galaxy filaments, the expansion of space becomes most apparent. Here, the Hubble flow dominates, with any 2 points growing steadily farther apart as new space appears between them. A civilization located in one of these cosmic deserts would have a very different perspective on the universe than we do, seeing far fewer nearby galaxies and experiencing cosmic expansion as the primary feature of their environment. The magnetic fields threading through intergalactic space are incredibly weak by earthly standards, millions of times weaker than a typical refrigerator magnet. Yet they extend across such vast distances that their total influence is enormous. These fields may have been created by the first stars and galaxies, spreading outward through space over billions of years, creating an invisible cosmic infrastructure that helps channel the flow of matter and energy. Some regions of intergalactic space contain virtually nothing but dark matter and dark energy, with ordinary matter so sparse that atoms are separated by distances measured in meters rather than microscopic scales. In these regions, the universe exists in its most pristine state, largely unchanged, since the early epochs of cosmic history. Here, space itself is the dominant feature, quietly expanding according to the laws of general relativity. The cosmic web continues to evolve even today, with new structures forming as matter flows along dark matter filaments toward the intersections where galaxy clusters grow. This process will continue for billions of years, gradually building ever larger structures while the expansion of space slowly works to pull everything apart. We exist during a brief window when both processes are active, creating the complex, beautiful architecture we observe today. Deep within the largest cosmic voids, where galaxies are separated by hundreds of millions of light-years, time itself seems to slow to a cosmic crawl. Here, the Hubble expansion dominates so completely that any 2 points in space grow steadily farther apart, not through any force pushing them, but simply because new space appears between them. If you could mark 2 positions in such a void and return millions of years later, you would find them significantly farther apart, with nothing having moved, the universe simply having grown larger around them. These supervoids represent the universe in its most serene state. The Bootes void, one of the largest known, spans 330 million light-years across, and contains almost nothing, fewer than a dozen galaxies where a typical region of space might contain thousands. An observer placed at its center would see darkness in almost every direction, with the nearest galaxies so distant they would be invisible to the naked eye. The night sky would be almost perfectly black, save for the faint afterglow of creation itself. Yet even in these seemingly empty regions, the universe maintains its subtle activity. Quantum fields fluctuate at the smallest scales, creating tiny temporary disturbances in the fabric of space-time itself. Virtual particles pop briefly into existence before cancelling each other out, a process so rapid and ephemeral that it exists below the threshold of direct observation, yet represents the baseline energy state of the vacuum itself. The cosmic microwave background radiation bathes these empty regions in the universe's most ancient light, photons that have been traveling for over 13.8 billion years since the epoch of recombination, when the universe first became transparent. This radiation carries information about the universe when it was only 380,000 years old, encoded in tiny temperature variations that map the density fluctuations that would eventually grow into all large-scale structure. As we float through these cosmic deserts, consider the extraordinary journey of this ancient light. When these photons began their travels, the universe was a hot, dense plasma, with a temperature of about 3,000 degrees, hot enough to glow like a light bulb filament. But as space expanded, the light was stretched to longer and longer wavelengths, cooling as it traveled, until today it appears as microwaves with a temperature of just 2.7 degrees above absolute zero. This cosmic background radiation is remarkably uniform, varying by only tiny amounts across the sky. Yet these minute differences of just a few parts in 100,018, contain the seeds of everything we see today. Regions that were slightly denser than average eventually collapsed under their own gravity to form the first stars and galaxies, while slightly less dense regions expanded into the vast voids we're imagining ourselves within. The polarization patterns in this ancient light tell us even more about the early universe. Like sunlight reflecting off a lake, the cosmic microwave background carries information about conditions at the moment of its emission. Scientists can decode these patterns to learn about the first moments after the Big Bang, when the universe underwent a period of rapid expansion called cosmic inflation that stretched quantum fluctuations to cosmic scales. Floating in the deep void between galaxy clusters, you would be surrounded by one of the most remarkable substances in the universe: dark energy. This mysterious component makes up about 68% of all energy in the cosmos, yet it reveals itself only through its effect on the expansion of space. Unlike matter or radiation, dark energy doesn't dilute as the universe grows larger. Instead, it maintains constant density even as new space appears, meaning its total influence grows stronger over time. Dark energy behaves like a kind of cosmic anti-gravity, not pulling things together but pushing space itself to expand faster and faster. The acceleration it drives is incredibly gentle, so gradual that it would be imperceptible over human timescales, yet so persistent that it will ultimately determine the fate of the entire universe. In the far future, trillions of years from now, dark energy will drive galaxies so far apart that each one will exist in isolation, surrounded by empty space that expands faster than light can cross it. But that future is unimaginably distant. For now, we exist in what cosmologists call the matter-dominated era, when the gravitational attraction of dark matter and ordinary matter can still overcome cosmic expansion on local scales. This allows galaxies to form and evolve, stars to ignite and shine, planets to coalesce, and life to emerge and contemplate its own existence. The dark matter that surrounds us in these void regions is equally mysterious but somewhat more familiar in its behavior. Unlike ordinary matter, dark matter doesn't interact electromagnetically. It doesn't absorb, emit, or reflect light. It reveals itself only through gravity, creating the invisible scaffolding around which all visible structure formed. In the cosmic web, dark matter filaments act like highways along which ordinary matter flows, channeling gas toward the intersections where galaxies grow. Computer simulations of cosmic evolution show dark matter organizing itself into a hierarchy of structures, from tiny clumps no larger than Earth to vast halos containing entire galaxy clusters. These simulations reveal the universe as a kind of cosmic city, with dense nodes connected by elongated filaments and separated by enormous empty regions. The pattern resembles neural networks, river systems, or the foam in a bathtub, suggesting some universal tendency for matter to organize itself into similar patterns across all scales. The largest dark matter halos in the universe surround galaxy clusters, extending far beyond the visible galaxies they contain. These halos are so massive that they bend and distort the light from more distant galaxies, creating gravitational lenses that allow astronomers to map the distribution of invisible matter. Through these cosmic magnifying glasses, we can see galaxies that would otherwise be too faint to detect, stretched and multiplied into beautiful arcs and rings around the intervening clusters. Within the voids themselves, dark matter exists at its lowest density, creating regions where the cosmic web is most tenuous. Here, the dark matter distribution resembles a ghostly mist, present but barely concentrated enough to influence the motion of the few atoms that drift through these spaces. The gravitational field in void centers is so weak that it would take billions of years for even a small perturbation to grow into anything resembling a galaxy. Yet voids are not completely empty. Careful observations reveal thin filaments of gas stretching between distant galaxies, glowing faintly in the light of hydrogen atoms excited by cosmic radiation. These intergalactic medium clouds represent the leftover material from galaxy formation, gradually being stripped away by stellar winds and supernova explosions and dispersed into the cosmic web. The temperature of gas in these void regions reflects the gentle violence of cosmic evolution, heated to millions of degrees by shock waves from structure formation. This thin plasma glows faintly in X-rays, while remaining so tenuous that it would feel like perfect vacuum to any material object passing through it. The dichotomy between extreme temperature and extreme emptiness represents one of the universe's most subtle paradoxes, matter that is simultaneously incredibly hot and incredibly sparse. Neutrinos stream through these regions in vast numbers, largely unaffected by the ordinary and dark matter around them. Created in stellar cores, cosmic ray interactions, and the Big Bang itself, neutrinos travel at nearly the speed of light, interacting so weakly with matter that they can pass through entire planets without stopping. Every second, trillions of neutrinos from the Sun alone pass through your body, most of them continuing onward through the Earth and out into space without leaving any trace of their passage. Some of these neutrinos are cosmic relics, created when the universe was only 1 second old and still hot enough for nuclear reactions to forge the first light elements. These relic neutrinos now fill all of space with a background radiation, even more ancient than the cosmic microwave background, cooled by cosmic expansion to temperatures near absolute zero but still carrying information about the universe's earliest moments. The cosmic neutrino background represents one of the most direct connections we have to the Big Bang itself, while the cosmic microwave background shows us the universe at 380,000 years old. Neutrinos decouple from other matter when the universe was only 1 second old, preserving information about conditions during the first moments of cosmic evolution. Though these relic neutrinos are currently too low in energy to detect directly, future experiments may eventually observe them, opening a new window into the universe's birth. Between the galaxies, space itself participates in the cosmic expansion in ways that challenge our everyday intuitions about motion and distance. When astronomers measure the recession velocity of distant galaxies, they're not measuring motion through space, but rather the expansion of space itself. The galaxies aren't racing away from us. Instead, new space is being created between us and them, carrying them along like boats on a river that's growing wider. This expansion means that light from distant galaxies is stretched as it travels toward us, shifting toward longer, redder wavelengths in proportion to the distance it has traveled. The most distant galaxies we can observe appear shifted so far into the red that their visible light reaches us as infrared radiation, requiring special telescopes to detect. Some galaxies are so distant that their light appears shifted beyond even infrared wavelengths, becoming detectable only in radio waves. The stretching of light by cosmic expansion also affects its energy. Photons from distant galaxies arrive with less energy than when they were emitted, their wavelength stretched by the expansion of space during their billion-year journeys. This cosmic redshift provides one of our most direct measurements of how the universe has expanded over cosmic time, allowing astronomers to trace the history of cosmic expansion back to when the universe was only a small fraction of its current size. In the deepest regions of intergalactic space, where the cosmic web is most tenuous, the expansion of space becomes the dominant feature of the environment. Here, the Hubble flow carries any test particles steadily apart, creating more distance between them without requiring any force or energy. It's as if space itself is the active agent, quietly creating more of itself according to the equations of general relativity. This expansion is not occurring into anything minds. There is no external space that the universe is expanding into. Rather, the universe is all there is, and it's creating more of itself as it evolves. The concept challenges our normal thinking about space as a container for things, revealing instead that space is itself a dynamical entity, responding to the matter and energy it contains according to Einstein's field equations. The rate of expansion varies depending on the contents of the universe. In the early cosmos, when matter and radiation dominated, expansion slowed over time as gravity worked to pull everything back together. But about 5 billion years ago, when the universe had expanded enough that dark energy became the dominant component, expansion began to accelerate. This transition marks a fundamental change in the universe's evolution, shifting from a cosmos fighting against its own expansion to one actively accelerating that expansion. Current observations suggest that this acceleration will continue indefinitely, leading to what cosmologists call the Big Rip scenario. In this far future, about 22 billion years from now, the acceleration will become so extreme that it tears apart first galaxy clusters, then galaxies, then stars, then planets, then atoms themselves. But this apocalyptic ending is so far in the future that it's scarcely meaningful compared to any human timescale. The universe will have expanded by more than a factor of 100 billion before reaching such extremes. For now, we exist in a cosmic sweet spot where expansion is gentle enough to allow complex structures to form and evolve. The delicate balance between gravity trying to pull things together and cosmic expansion trying to pull them apart creates the dynamic tension that drives galaxy formation, stellar evolution, and ultimately the chemistry of life itself. The magnetic fields threading through intergalactic space add another layer of subtle complexity to these seemingly empty regions. These fields are incredibly weak by earthly standards, about 1,000,000 times weaker than Earth's magnetic field, yet they extend across distances so vast that their total energy content is enormous. Created by the first stars and galaxies, these magnetic fields have been growing and evolving for billions of years, creating an invisible infrastructure that influences the flow of charged particles across cosmic distances. Cosmic rays, high-energy particles accelerated by supernova explosions, black holes, and other violent cosmic phenomena, follow these magnetic field lines as they travel through intergalactic space, like charged particles spiraling around the magnetic field lines in Earth's radiation belts. Cosmic rays wind their way along the cosmic web's magnetic highways, sometimes taking detours that extend their journeys by millions of light years. The interaction between cosmic rays and magnetic fields creates one of the universe's most beautiful phenomena, the radio emission that fills all of space with a gentle background glow. This synchrotron radiation, produced when charged particles spiral around magnetic field lines, creates a cosmic radio background that tells the story of high-energy processes throughout the universe's history. Some cosmic ray particles have energies so extreme that they approach the fundamental limits imposed by physics itself. These ultra-high energy particles carry more energy than we can produce in our most powerful particle accelerators, and their origins remain mysterious. They may come from the most violent events in the universe, colliding black holes, gamma-ray bursts, or exotic phenomena we don't yet understand. When these particles finally collide with Earth's atmosphere after journeys that may have lasted millions of years, they create cascades of secondary particles that rain down over areas the size of cities. The study of these cosmic messengers provides one of our few direct ways of probing the physical conditions in the deepest reaches of space. Unlike light, which can be absorbed or scattered by intervening matter, the highest energy cosmic rays travel essentially unimpeded across intergalactic distances, carrying information about their sources directly to our detectors. Between the cosmic ray particles and the magnetic fields, between the streaming neutrinos and the expanding space, between the dark matter scaffolding and the ancient photons of the cosmic microwave background, the empty regions of the universe reveal themselves to be anything but empty. They're filled with invisible rivers of matter and energy, all flowing according to the fundamental laws of physics in a grand cosmic symphony that has been playing for nearly 14 billion years. The gravitational waves that Einstein predicted and that we've only recently learned to detect also propagate through these intergalactic regions, carrying information about some of the most violent events in cosmic history. When black holes collide or neutron stars merge, they create ripples in spacetime itself that travel outward at the speed of light, stretching and compressing space by amounts smaller than a proton over distances of millions of light years. These gravitational waves pass through the cosmic voids essentially unchanged, providing a new way to observe the universe that's completely independent of electromagnetic radiation. Unlike light, which can be absorbed, scattered, or redshifted by intervening matter, gravitational waves travel through the universe virtually unimpeded, carrying pristine information about their sources across billions of light years. The detection of gravitational waves has opened an entirely new window into cosmic phenomena, allowing us to hear the universe in addition to seeing it. The collisions of black holes produce gravitational wave signatures that sound like chirps when converted to audio, with the frequency and amplitude encoding information about the masses and spins of the colliding objects. These cosmic collisions, violent beyond imagination, create disturbances in spacetime that we can detect as whispers of motion smaller than 1,000th the width of a proton. As our imaginary journey through the cosmic voids continues, we encounter regions where the very concept of direction becomes meaningless. So far from any significant gravitational sources, with galaxies hundreds of millions of light-years away in every direction, there is no up or down, no north or south. The only reference frame is provided by the cosmic microwave background itself, which defines a kind of universal rest frame against which all motion can be measured. This cosmic rest frame reveals that our local group of galaxies is moving at about 630 kilometers per second relative to the cosmic microwave background, carried along by the gravitational influence of massive structures like the Virgo cluster and more distant attractors. This motion creates a slight asymmetry in the temperature of the cosmic microwave background. It appears slightly warmer in the direction we're moving toward and slightly cooler in the direction we're moving away from, like the Doppler shift of sound waves from a moving source. The cosmic microwave background thus serves as the universe's ultimate GPS system, providing a reference frame that exists everywhere and against which all motion can be measured. It's as if the universe comes equipped with its own coordinate system, written in the language of ancient light that fills every cubic centimeter of space. In the deepest voids, where this ancient light has traveled unimpeded for billions of years, it carries the most pristine information about the early universe. Free from contamination by local sources of radiation, the cosmic microwave background in these regions provides our clearest view of conditions when the universe was young. The tiny temperature fluctuations in this radiation map out the density variations that would eventually grow into all the structures we see today. These primordial fluctuations were likely created during the first fraction of a second after the Big Bang, when the universe underwent a period of exponential expansion called cosmic inflation. During this brief epoch, quantum fluctuations in the fields driving inflation were stretched to cosmic scales, creating the seeds of all future structure. The fact that we can still observe these quantum fingerprints in the cosmic microwave background represents one of the most remarkable connections between the smallest and largest scales in physics. The polarization patterns in the cosmic microwave background carry even more information about the early universe. Like sunlight scattered by Earth's atmosphere, the cosmic microwave background was polarized by its last interactions with matter before the universe became transparent. These polarization patterns preserve information about the motion of matter at the time of recombination and potentially about gravitational waves created during cosmic inflation itself. Future observations of cosmic microwave background polarization may allow us to peer even further back in cosmic history, potentially detecting the gravitational wave signature of inflation itself. Such a discovery would provide direct evidence for the process that created the initial conditions for all subsequent cosmic evolution, linking the quantum realm of the very early universe to the large-scale structure we observe today. The cosmic web that connects all matter in the universe operates like a vast hydraulic system, channeling the flow of gas and dark matter along its filaments toward the nodes where galaxies form. This process has been ongoing for over 13 billion years, gradually building the hierarchy of structures we observe today. The largest nodes in this network are galaxy clusters containing thousands of individual galaxies bound together by gravity and surrounded by halos of dark matter extending for millions of light years. Between these massive clusters lie the filaments and voids that make up most of the universe's volume. The filaments, traced by chains of galaxies and streams of hot gas, contain most of the universe's ordinary matter outside of galaxies themselves. The voids, by contrast, contain almost nothing. They represent the universe in its most pristine state, largely unchanged since the early epochs of cosmic history. The contrast between these dense filaments and empty voids creates the universe's most striking large-scale feature, a cosmic web that resembles a three-dimensional version of soap bubble foam, with dense walls and filaments surrounding vast empty regions. This structure emerged naturally from the gravitational amplification of tiny initial density fluctuations, demonstrating how simple physical laws can create complex, beautiful patterns when operating over cosmic scales and timescales. The evolution of this cosmic web is far from over. Computer simulations of future cosmic evolution show the structure continuing to grow and evolve for billions of years to come, with smaller structures merging to form ever larger ones, while the expansion of space gradually works to pull everything apart. We exist during a special epoch when both processes are active, creating the dynamic, evolving universe we observe today. The dark energy driving cosmic acceleration will eventually win this competition, pulling galaxy clusters apart faster than gravity can hold them together. In the far future, each surviving galaxy will find itself alone in an expanding sea of space, with its nearest neighbors receding beyond the horizon of observability. The cosmic web will dissolve, leaving isolated islands of matter surrounded by ever-growing oceans of empty space. But that future is inconceivably distant, trillions of times longer than the current age of the universe. For now, we can contemplate the cosmic web in all its current glory, marveling at the way simple physical laws have created such intricate, beautiful structure from the nearly uniform initial conditions of the early universe. The quantum nature of reality adds yet another layer of subtlety to these cosmic voids. Even in the apparent emptiness between galaxies, quantum field fluctuations ensure that space is never truly empty. The Heisenberg uncertainty principle allows energy to be borrowed from the vacuum for brief moments, creating virtual particle pairs that pop into existence and immediately annihilate each other. These quantum fluctuations operate at scales so small and timescales so brief that they normally have no observable effects on macroscopic objects, but they represent the fundamental quantum foam that underlies all of space-time, creating a subtle graininess at the smallest scales that may someday be detectable by sufficiently sensitive experiments. In regions where space-time is curved by massive objects like black holes, these quantum fluctuations can have more dramatic effects. Near black hole event horizons, the intense gravitational fields can separate virtual particle pairs before they can annihilate, causing one particle to fall into the black hole while the other escapes as real radiation. This Hawking radiation represents one of the most profound connections between quantum mechanics, gravity, and thermodynamics, suggesting that black holes have temperatures and can eventually evaporate completely. The same quantum processes that create Hawking radiation also ensure that even the most perfect vacuum is alive with constant activity at the smallest scales. Empty space seethes with virtual particles, quantum field fluctuations, and zero-point energy that can never be completely removed. In this sense, the vacuum itself is one of the most complex and mysterious entities in physics, deserving of as much study and wonder as any exotic cosmic phenomenon. The cosmic voids we're imagining ourselves floating through represent the closest thing to perfect vacuum that exists in nature, yet even they are filled with this quantum activity. Here, in the most pristine regions of the universe, space itself demonstrates its fundamental quantum nature, maintaining a baseline level of activity that connects these seemingly empty regions to the deepest mysteries of physics. As we contemplate these vast scales and subtle phenomena, it's worth remembering that our ability to understand and appreciate them represents something truly extraordinary. The human brain, a 3-pound collection of atoms that organized themselves over billions of years of cosmic and biological evolution, can contemplate the origin and fate of the entire universe. We are, quite literally, the cosmos reflecting on itself. Nice star stuff arranged in such a way that it can ponder its own existence and meaning. As our imaginary journey through deep space draws toward its end, consider the profound quietude of these vast regions. Here, in the spaces between galaxies, the universe reveals its most contemplative aspect. Free from the busy activity of star formation and stellar evolution, free from the complex chemistry of planetary surfaces, space itself becomes a meditation on existence, expansion, and the deep structures that connect everything. The story of the cosmic voids is also intimately connected to our own story. The atoms in your body were forged in stellar cores that formed within the cosmic web, in galaxies that condensed from gas flowing along dark matter filaments. The oxygen you breathe, the carbon in your DNA, the iron in your blood, all of these elements were created when massive stars collapsed and exploded as supernovas, dispersing their nuclear furnace products into the intergalactic medium. These stellar explosions didn't just create the elements of life minds, they also helped sculpt the cosmic web itself. The energy released by supernovas and stellar winds pushed gas out of galaxies and into the spaces between them, creating bubbles and cavities in the intergalactic medium. Over billions of years, these processes helped define the boundaries between dense galactic regions and empty voids, shaping the large-scale structure we observe today. The cycle of matter between galaxies and the intergalactic medium continues today. Gas falls into galaxies along cosmic web filaments, gets processed through stars and stellar explosions, then gets expelled back into intergalactic space, enriched with the heavy elements created in stellar cores. This cosmic recycling program has been operating for over 13 billion years, gradually increasing the chemical complexity of the universe and making possible the rich chemistry required for life. Some of the gas in intergalactic space has never been inside a galaxy at all. These are the remnants of the primordial hydrogen and helium created in the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear fusion to occur. This primordial gas retains the signature of Big Bang nucleosynthesis, roughly 75% hydrogen and 25% helium, with trace amounts of lithium and other light elements. The detection of this primordial composition in intergalactic gas clouds provides one of our strongest pieces of evidence for the Big Bang theory. The precise ratios of light elements match exactly what nuclear physics predicts should have been created when the universe was between 10 seconds and 20 minutes old, during the brief window when conditions were just right for nuclear fusion, but before the universe had cooled too much for these reactions to continue. These ancient gas clouds floating in the cosmic web for billions of years preserve information about the universe when it was incredibly young and simple compared to today. They represent cosmic fossils, unchanged samples of the universe's primitive composition that allow us to directly observe and analyze matter from the earliest epochs of cosmic history. The intergalactic medium also carries the signature of more recent cosmic events. When galaxies collide and merge, the process strips gas from both systems and disperses it into surrounding space. When supermassive black holes at galactic centers become active, they can blow enormous bubbles of hot gas that extend far beyond their host galaxies. These energetic processes create a complex tapestry of hot and cold regions in intergalactic space, each telling the story of cosmic violence and evolution. The radio waves that fill intergalactic space carry information about these high-energy processes. Synchrotron radiation from relativistic particles spiraling around magnetic field lines creates a background glow that traces the history of cosmic ray acceleration throughout the universe. This radio background is extremely faint, but sensitive telescopes can detect it and use it to map the invisible magnetic infrastructure of the cosmic web. The polarization of this radio emission reveals the structure and strength of intergalactic magnetic fields, providing crucial information about how these fields formed and evolved. Current observations suggest that intergalactic magnetic fields may have been created very early in cosmic history, possibly during the epoch of inflation itself, then gradually amplified by the dynamo action of moving plasma in the cosmic web. These magnetic fields play a crucial role in the propagation of cosmic rays through intergalactic space. High-energy particles from distant galaxies follow the magnetic field lines like tracks, sometimes taking circuitous routes that can extend their journeys by factors of thousands. The highest energy cosmic rays, with energies approaching fundamental physical limits, may be the only particles capable of traveling in straight lines across intergalactic distances. The interaction between cosmic rays and the cosmic microwave background radiation creates another subtle effect that shapes the high-energy particle environment of intergalactic space. When ultra-high-energy cosmic ray protons collide with cosmic microwave background photons, they can create particles called pions that quickly decay into other particles, including neutrinos. This process, called the GZK cutoff, effectively limits how far the highest energy cosmic rays can travel before losing their energy. This means that the most energetic cosmic rays we detect on Earth must come from relatively nearby sources, within about 100 million light-years, which is nearby by cosmic standards, but still represents a vast volume of space containing thousands of galaxies. The search for the sources of these ultra-high-energy particles continues to challenge our understanding of the most extreme acceleration processes in the universe. The cosmic web itself may play a role in accelerating particles to these extreme energies. Computer simulations suggest that the shockwaves created when cosmic web filaments collide and merge could accelerate particles to energies far beyond what individual galaxies or even galaxy clusters can achieve. These cosmic web shocks would be some of the largest coherent structures in the universe, extending across hundreds of millions of light-years. The study of intergalactic space has revealed unexpected connections between the largest and smallest scales in physics. The same quantum field fluctuations that create virtual particles in laboratory vacuums also operate in the vast emptiness between galaxies. The same gravitational waves that we detect from colliding black holes also propagate through cosmic voids. These connections suggest that the universe operates as a unified system, with phenomena at every scale influenced by processes occurring at every other scale. The expansion of space affects the behavior of quantum fields. While quantum processes in the early universe created the initial conditions for all large-scale structure, the deaths of massive stars create the heavy elements that make life possible, while living beings like ourselves have evolved the ability to study and understand the cosmos that created them. The temperature of intergalactic space tells its own story of cosmic evolution. In the densest parts of the cosmic web, where gas flows along filaments toward galaxy clusters, temperatures can reach millions of degrees as gravitational energy is converted to heat. In the emptiest voids, temperatures approach the cosmic microwave background limit of 2.7 Kelvin, representing the coldest naturally occurring environments in the universe. This temperature structure traces the history of cosmic structure formation. Regions that collapsed early under gravity experienced more violent heating, while regions that remained under dense expanded along with the universe and cooled adiabatically. The result is a complex thermal map of the universe that preserves information about when and how different regions began to collapse under their own gravity. The future evolution of intergalactic space will be dominated by the ongoing acceleration of cosmic expansion. As dark energy continues to drive galaxies apart, the density of matter in intergalactic space will continue to decrease, approaching ever closer to perfect vacuum. The cosmic microwave background will continue to cool as the universe expands, eventually reaching temperatures indistinguishable from absolute zero. In the far future, when the last stars have burned out and black holes have evaporated through Hawking radiation, intergalactic space will become the dominant environment in the universe. It will be a realm of perfect darkness and cold, filled only with elementary particles, photons, and the quantum fluctuations of empty space. Yet even in this ultimate state, the universe will maintain its subtle beauty, a vast, quiet meditation on the deep structures of physics and mathematics. The cosmic microwave background that currently fills all of space will continue to exist even in this far future, though it will be redshifted to such long wavelengths that its photons will be separated by distances larger than galaxies. These ancient photons, the last remnants of the hot Big Bang, will continue their eternal journey through space, carrying information about the universe's birth into a future so distant it challenges comprehension. But these considerations of the universe's ultimate fate only enhance our appreciation for the current epoch. We exist during a brief, shining moment in cosmic history, when the universe is complex enough for consciousness to emerge and contemplate its own existence. The same processes that created the cosmic web and filled intergalactic space with subtle phenomena also made possible the emergence of life, intelligence, and the capacity for wonder that allows us to appreciate the beauty of it all. The very fact that we can imagine floating through intergalactic space, that we can understand the physics of cosmic expansion and dark energy, that we can detect gravitational waves and cosmic rays and ancient photons from the Big Bang itself, all of this represents a remarkable achievement of cosmic evolution. Matter has organized itself in such a way that it can study and understand the very cosmos that created it. As we prepare to return from our imaginary journey through the cosmic voids, take a moment to appreciate the profound interconnectedness of everything. The quantum vacuum fluctuations that fill empty space are governed by the same physical laws that describe the behavior of atoms in your body. The gravitational waves that propagate through intergalactic space are described by the same equations that govern the curvature of space-time around the Earth. The cosmic expansion that drives galaxies apart is the same process that determines the ultimate fate of everything. You are not separate from these cosmic processes. You are an expression of them. The atoms in your body have traveled through intergalactic space, been processed through stellar cores, and participated in the cosmic web's evolution for billions of years before finally organizing themselves into the patterns that constitute your consciousness. Your thoughts about the cosmos are the cosmos thinking about itself, using structures that emerged from the same fundamental physical processes that created galaxies, stars, and planets. The darkness between galaxies is not empty darkness. It's filled with invisible rivers of dark matter, ancient light from the cosmic dawn, magnetic fields that stretch across millions of light years, and the gentle pressure of dark energy creating new space with each passing moment. Even in apparent nothingness, the universe maintains its subtle complexity, its quiet creativity, its patient work of cosmic evolution. From this perspective, floating between galaxies, Earth would be completely invisible, our entire solar system lost in the light of one ordinary star among hundreds of billions. Yet this doesn't diminish our significance. Instead, it highlights the extraordinary nature of our existence. In all this vastness, in all this cosmic quietude, matter has organized itself into forms capable of contemplating the very cosmos that created them. We are not separate from the universe, but expressions of its deepest creativity. The silence of space, the patient expansion of the cosmic web, the gentle dance of dark matter and dark energy, the ancient light still traveling from the dawn of time, all of these phenomena invite us into a different relationship with scale, with time, with our place in the grand scheme of things. They remind us that we are part of something much larger than ourselves, while simultaneously celebrating the remarkable fact that the universe has evolved conscious observers capable of appreciating its beauty. As you drift towards sleep tonight, perhaps you can carry with you this sense of cosmic perspective. Your physical body is made of atoms forged in stellar cores, Your consciousness is a temporary arrangement of matter and energy that has emerged from billions of years of cosmic evolution, and your dreams will unfold in a mind that represents the universe's way of experiencing itself subjectively. The vast spaces between galaxies will continue their patient expansion throughout the night. Dark matter will maintain its invisible scaffolding, ancient light will continue its billion-year journeys across the cosmos, and in the morning when you wake, you'll still be traveling through space at thousands of miles per second, spinning on a planet that orbits a star that orbits a galaxy that moves through the cosmic web toward gravitational attractors so distant they challenge comprehension. But for now, it's enough to simply rest in the knowledge that you are part of this magnificent cosmic story, that your consciousness represents matter and energy arranged in such a way that the universe can contemplate its own beauty, and that the same physical laws governing the expansion of space and the dance of galaxies also govern the gentle rhythm of your breathing as you settle into sleep. Thank you for joining me on this journey through the peaceful depths of space. Thank you for your time, your attention, and your willingness to contemplate the cosmos with wonder and curiosity. If you enjoyed this exploration, please consider subscribing to Sleep About Science, and feel free to let me know in the comments where in the world you're listening from minus. I love knowing that these words are reaching fellow cosmic travelers across the globe. Sweet dreams, fellow star stuff. May your sleep be as peaceful as the vast spaces between galaxies, as quiet as the cosmic void, and as filled with potential as the quantum foam that underlies all reality. Until next time, sleep well and remember, you are the universe experiencing itself subjectively, and that is perhaps the most remarkable fact of all. Good night.